In this video, I'm going to start talking about the atom. So remember, all elements are made of atoms. There is no, for instance, elements made out of just electrons. So atoms are the smallest unit of what the elements are made out of. So these are the smallest particles that have the properties of the element. And this was first put forward by the Greek philosophers who called these atomos, which just means that it's indivisible. But later on in 1808, the atomic theory was proposed by John Dalton. His atomic theory has several postulates, and so the first one is that all matter is made up of tiny particles called atoms, and the second one is that all atoms of a given element are identical to one another and different from atoms of other elements. So, for instance, if you have carbon atoms, two carbon atoms are identical to each other, but a carbon atom and a nitrogen atom are not identical to each other. There isn't any such thing as two different types of carbon atoms that are not identical to each other. As we'll see later on in this video, there are things called isotopes, which allows some small variation, but for the atomic theory that Dalton came up with, the second postulate was that all atoms of a given element are identical to one another and different from atoms of other elements. The third postulate was that atoms of two or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and the same number of each kind. And so, for instance, water is always made out of oxygen and two hydrogens. It's always those two elements combined in those proportions. So if it has different elements or if it has different proportions, then it is not water. So water is just defined by the fact that it is made out of one oxygen and two hydrogens. And so that is regardless of what phase the water is in. The fourth one is that a chemical reaction involves the rearrangement, separation, or combination of atoms. So atoms are never created or destroyed during a chemical reaction. For instance, combustion of methane, all we're doing is just rearranging and recombining the atoms. There's no new atoms that are being created, and none of the atoms are being destroyed. Similarly, with synthesis of ammonia, we just are rearranging these hydrogens and nitrogens. There's no nitrogens being created or destroyed, no hydrogens being created or destroyed. Everything is always preserved, and it's just a rearrangement of what things are bound to what other things. So by the end of the 1800s, scientists were then able to show that the atom was actually composed of smaller particles, and these are called subatomic particles, and these are the small bits of matter that atoms are made of. Subatomic particles have their own unique properties, but they do not have the properties of a particular element. And the subatomic particles are the proton, the electron, and the neutron. When we look at each of these particles, for instance, the proton is going to have a positive 1 charge. It has a mass of 1.673 times 10 to the negative 24 grams. It has an atomic mass unit of 1.007. So the atomic mass unit was defined earlier than when we had the more precise and sophisticated measuring instruments than we do now, and it was defined so that a proton was equal to 1, but it has later been found that the proton is actually slightly heavier than that. And so that's why it's very close to 1, but it's not exactly 1. And these are located in the nucleus of the atom. Neutrons, which have 0 electric charge, are ever so slightly heavier than the proton. So we can see instead of 1.673, it's 1.675 times 10 to the negative 24 grams, and has 1.008 atomic mass units. And these are also found in the nucleus. Then the electron, which has a negative 1 charge, are quite a bit lighter than both the proton and the neutron. So we see this is on the order of 10 to the negative 28 rather than 10 to the negative 24. So 4 orders of magnitude lighter. And so we also see that reflected in the atomic mass units for it. And these are outside the nucleus. So one of the things that we will notice is that because the electrons are so much lighter than the proton and the neutron, we oftentimes do not take them into consideration when we are coming up with the mass of an atom. So since each proton has a +1 charge and each electron a -1 charge, if the number of protons is equal to the number of electrons, then the overall atom has a charge of 0. Consider, for instance, carbon, which has 6 protons and 6 electrons. We can think about it this way. If we take one of the electrons and one of the protons, they cancel each other out as far as their charge goes. And so there's zero net charge there. We take the second pair, those also cancel out. The third pair cancel out. The fourth pair cancel out. The fifth pair cancel out. And the sixth pair cancel out. And so what that means is that all the charges have canceled, and so there is no net charge. There is zero net charge. And so when we are talking about neutral atoms, we're talking about ones that have an equal number of protons and electrons. And that means their charges completely cancel each other out, and so there is no net charge for it. Another way we can think about it is we're essentially just taking a +1 and a -1 and then adding 6 of those up. And so each one of these +1s and -1s is 0. So if you just add 0 6 times, then you're getting 0 overall. So the atomic number and the mass number help us determine the numbers of subatomic particles within an atom of each element. So you must be able to find these atomic number and mass numbers of an element on the periodic table and in what's called a nuclear symbol. So that looks like this. If you look at the periodic table, you will see something that looks kind of like what's on the left here. But then the nuclear symbol looks like this, where we have the carbon here, so that's the C for carbon. Then we have that 12 in the upper left and the 6 in the bottom left. And so the bottom left there is our atomic number, and that is the number of protons that it has. Where then the mass number goes up here. What you'll notice is that on the periodic table, these are not whole numbers, and we'll talk about more of that at the end of this video when we talk about how we actually come up with those numbers. But the mass number on the nuclear symbol will always be some whole number, and this will get into what's called isotopes that we'll talk about here in a minute. Then we put the charge there. We've talked about how there is zero charge if the number of protons is equal to the number of electrons. In a future video, we'll talk about when this is not the case, and we actually have a non-zero charge, and those are called isotopes. But for our purposes right now, we can just say that this has a zero charge. And then this is the number of atoms, and that will become important in even later videos when we start talking about molecules and how we combine these things together, and this just tells us how many of these things there are. And so remember, the atomic number of an element is equal to the number of protons within every atom of that element. So the atomic number is equal to the number of protons, meaning that carbon always has 6 protons. There's no such thing as carbon with 5 protons or carbon with 7 protons. It always has 6, and anything that has only 6 protons is just going to be carbon. That's literally how it's defined, these elements. We define it by the number of protons that they have. So just keep that in mind, that the atomic number is always equal to the number of protons. So that will mean that every atom of a single element will have the same number of protons. Atoms of different elements will have different numbers of protons, and different elements have different atomic numbers, since remember, the atomic number just is the number of protons. Atomic number can be found above the chemical symbol in the periodic table, or it can be found in the lower left side of the nuclear symbol. So the atomic number of an element, as I keep stressing, is equal to the number of protons within every atom of that element. Atoms of different elements will have different numbers of protons. So for instance, lithium has 3 protons. Carbon has 6 protons. So you'll never have a carbon with 3 protons. You'll never have a lithium with 6 protons, and so on and so forth. And when the atom is neutral, that just means that the number of protons is equal to the number of electrons. So as discussed earlier, they all cancel out. And remember, I said that the electrons are not taken into consideration when we come up with the mass of these things. So the mass of an atom comes from the protons and neutrons. So the mass number is just the number of protons plus the number of neutrons. So we do not want to use the mass in the periodic table, which we'll discuss later where that number comes from. But when we're coming up with our mass number, we don't want to use those numbers. So we want to use the mass number in the upper left side of the nuclear symbol. So the mass number of an element, like I said, equal to the sum of the protons and the neutrons of the atom. So for instance, we have hydrogen here. If the atomic number is 1, and the mass number is 1, that means we have just 1 proton and 0 neutrons, because the mass number is the number of protons plus the number of neutrons. So 1 plus 0 equals 1. And we would also have 1 electron, since we're talking about something with no charge here. Whereas if we have a carbon here, this has an atomic number of 6 and a mass number of 12. So that means we have 6 protons, and since the mass number is 12, we must also have 6 neutrons, and we would also have 6 electrons if we have no charge on it. Then something like copper has an atomic number of 29 and a mass number of 64. That means it has 29 protons, and it would have 64 minus the 29 number of neutrons, so that would be 35 neutrons. And then since we're talking about something with no charge, it must have 29 electrons as well. You are likely to see tables like this on assignments where you're supposed to fill in the blanks on the table. And so you're supposed to be able to come up with what the other things on the table are just based on the information given. And so for instance, this first one, we're looking at something that has the atomic symbol Al. And so what we want to do is look at the periodic table and see that this is going to be aluminum. And so we see that has 13 for the atomic number. And so the atomic number is just the number of protons, so we could put 13 for the number of protons in there. The neutron number is equal to the mass number, which was also given, minus the number of protons. So that means there would be 14 neutrons, and the number of protons, because we're just assuming that we're using neutral atoms here, is going to be equal to the number of electrons. So we could put 13 in also for the number of electrons. So we would get this right here. Then for the next one, it gives us the atomic number and the number of neutrons. So what we want to do is look for the atomic number on the periodic table. This time it's 12, so that would actually be magnesium. And so that means the atomic number being the number of protons means it has 12 protons. And the mass number being the proton number plus neutron number, which was also given, would give us 24 for the mass number. And again, we're assuming neutral, so proton number equals electron number, so 12 electrons. So we could fill this in on the table. The next one gives us potassium. It tells us the name of it, and it gives us the number of neutrons. So we want to look for potassium on the table. That's this one, and so we see that this has the symbol K. It's an atomic number of 19, which means that it also has 19 protons. And so to get the mass number, we take the number of protons plus the number of neutrons, and so that gives us 39 for the mass number. Then again, we're assuming neutral, so the number of electrons is also 19. So we can fill this in on the table. The next one just gives us the number of protons and the number of neutrons. So we remember that the number of protons is equal to the atomic number, so we just look for the atomic number 16, so that's sulfur. So that's symbol S with 16 protons. We get the mass number by adding the proton number plus neutron number to get 31 for our mass number. And then the proton number, again, equal to the electron number, so that's 16 electrons. We can put this into our table. The next one just gives us the mass number and the number of electrons. And so we, remember, are assuming neutral, so we can take 26 electrons to be equal to the number of protons. And so we look for what has 26 protons. That's iron, and so that means that we have 26 protons. The atomic number is equal to the number of protons. That's iron, symbol Fe. And the neutron number is equal to the mass number minus the proton number. So that gives us 30 neutrons. So we can put that into our table. And so we can see how we can come up with all of these other numbers and symbols just based on some limited information by understanding how these numbers and things on the periodic table actually work. So remember, I keep stressing this idea that all atoms of the same element have the same number of protons. So the number of protons is equal to the atomic number of the element. Atoms of the same element, as I said before, can have varied numbers of electrons. We'll talk about that more in a future video, but that just means that we have what's called an ion and would no longer have a charge of 0. But atoms of the same element can also have varied numbers of neutrons, and these are called isotopes. Atoms with different numbers of neutrons have different masses. So for instance, if we have oxygen 16, this has a mass of 15.994915, and so that has 8 neutrons, 8 protons, 8 electrons. But then we can also have oxygen 17, which has another neutron, so it has 9 neutrons, 8 protons, 8 electrons. But then we can also have oxygen 18, which has 10 neutrons, 8 protons, 8 electrons. So the two things to notice here, the number of protons does not change between these. The other thing to notice is the number of neutrons does change between these. So we can have different numbers of neutrons, which will change the mass. We can see the mass column here increases as we increase the number of neutrons, but the number of protons never changes. And so we can come up with different ways of actually showing these things, showing different isotopes for them. So for instance, if we have different isotopes of hydrogen, we would call it hydrogen 1, hydrogen 2, and hydrogen 3. So hydrogen 1 would have no neutrons because that 1 there is its mass number. And so it has to have 1 proton. So if it's hydrogen 1, it has 1 proton, 0 neutrons. Hydrogen 2 would have 1 proton, 1 neutron. Hydrogen 3, 1 proton, 2 neutrons. You can also use it like this, H1, H2, H3, or you can use the atomic symbol. And this is the one we've kind of looked at before, but you often see it written this way as well, like it is on the bottom. And that's because if we're talking about hydrogen, remember, hydrogen is just defined as the element that has 1 proton. And so that means that if we're talking about hydrogen, we already know that we're just talking about something with 1 proton. So that lower left number oftentimes gets left off of our nuclear symbol here. So what is the atomic mass of oxygen on the periodic table? So remember, I said when we come up with these mass numbers, we don't use the one that's on the periodic table, which oftentimes has a bunch of decimals to it. But how do people actually come up with that one on the periodic table? And so the atomic mass on the periodic table is what's called a weighted average of the masses of the naturally occurring isotopes. So to calculate the weighted atomic mass of an element, you need accurate masses, which is what we have in this column right here, and you need the abundances of all naturally occurring isotopes. So the abundance, when we're talking about that, is how much of each isotope actually shows up in nature. So if we're looking at something like chlorine here, this has this atomic mass of 35.45. And that's because most of the chlorine atoms are the 35 mass number here. So that means all those isotopes have a mass of 35. But then we see that some smaller percentage of them actually have a mass number of 37. And so that's why this would be slightly above 35, because there are some that are slightly heavier than that. And so that would sort of pull the mass higher than the 35. And so that's what we mean when we talk about the abundance here, is that there are differing amounts of these. So for instance, magnesium, we see that its mass right here, its atomic mass is 24.31. This one that's 24 is the most abundant, but we also have 25 and 26 on here. And so that's going to pull the weight higher than just 24. We also see that these abundances are given in percentages, but when we want to actually calculate the weighted average, we do need to turn those into proportions, and we do that by dividing the percentage by 100. So for instance, if we wanted to do this for oxygen, we would take this, these are our masses, and these are the abundances here in percentages. And so we would want to first take this one, so the mass multiplied by the abundance as a proportion. So we want to divide by 100. Then we add the next mass, and then multiply that by its abundance, and then we take that last mass and multiply that by its abundance. And so when we do that, we end up getting 15.999 AMU. And if you look at a periodic table, and it's going to be slightly different based on the periodic table you're looking at, a lot of them actually just round it up to 16.00. This one, we see that we can get it at 15.999, and you will also see that on some periodic tables. So it is going to be slightly different based on the periodic table, but it will be something very close to this. And so we can do the same thing with something like magnesium. So we first want to just add up all of the masses multiplied by their abundance, and then we can get that equal to the 24.31 AMU that you would see on a periodic table. We can also do this to solve for the mass of some of the isotopes here. So if we know what the total mass is, which you could get from the periodic table, you can use that with masses and abundances of other stuff and then just solve for the mass of one of the isotopes. So we could do it something like this. So we set it up where we put X in here for unknown. That's where the question marks are here. We don't know what the mass is for the silicon-29, so we want to solve for this X here. So we just do some algebra to it. We solve for the X. We get 28.978 AMU, where, by the way, AMU just stands for atomic mass unit. But then we see that this means that the mass of the silicon-29 is equal to 28.978 AMU. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.